we are going to look into digital logic, and I'm going to describe the logic gates to you, how they function, how we put them together, and but just before I start with that, I want to give you a little bit of an overview that will sort of give you an idea of where this digital logic, where these things actually are in a system. And so far away from the actual line conductors and the motor starters and the actual motors themselves, all of that stuff, there is typically some control wiring, and it usually goes into where the PLC is. Okay, so we have typically all sorts of controls, automated controls, but let me just give you this idea. To a PLC, you would have actually have inputs and outputs. And essentially what happens is these are normally fairly low voltage and current circuits, 120 volts or less. And your inputs will take, they could be analog inputs, they could be discrete, just 1 or 0. But in any case, once those signals have come in to the PLC, then they're actually converted inside into data registers, and that's done by a signal that is essentially 0 volts or 5 volts. And that's what's going to impress into the data register. So this is just a memory chip location, and it looks like this. I'll draw this a large scale of it. It essentially looks a little bit like this. You may have seen these. This is an IC, integrated circuit, and they look a little like centipedes, right? Now, depending on how big they are, they got a lot of pins on them underneath. So this is really just an integrated circuit, and inside of this, printed into the semiconductor material, are many, many gates. And so depending on what the inputs are to the PLC and how the program has been written, which is essentially how do you combine what's in these circuits, then there's some decisions that are made based on that, and then they turn on the outputs, and then we work our way up again. This may go through some relays, and then eventually to some contactors, and then may actually switch on some some thousands of volt motors, perhaps hundreds or thousands of horsepower. So all of this is controlled by something that is essentially the actual size of this. This is probably a big one right there. Okay, so very, very small components. And so what I want to show you then is I'm going to show you the gates, and then I'm going to show you a comparison of what a motor control circuit that we would have hardwired up would look like in comparison to that gate. And so let me start with this. First of all, the first of the gates that we want to talk about is, and I'm going to stir it over here, looks like this. It's called an AND gate. Okay, this is called AND. And what I'm going to show you is this. Now the gates have usually from one or two, sometimes 3 inputs on them. And gates always have 1 output, okay? So an output there. And we usually label these, there's no real specific way, but it's fairly common if you're starting at the beginning that you would label this as A and B. You can call this whatever you want. I'm going to call it Y. And these are inputs, and this is the output. Now, there's one thing that I want to point out right away, and this is not drawn onto every gate that you look at. But gates, if you take a chip let's say that I've got an IC here, and let's say that I've got some gates like this. And I'm just going to show a couple, okay? Input, input, and output. Now, for instance, this might come to a pin, this might come to a pin, so there'd be an actual pin that would correspond, right? This would come out, there'd be a pin here, that would be one, this would be one, and this would be one. So you can almost say, okay, if I wanted to, put inputs into this one, I got to connect up to these pins. Now, the other thing you got to realize is that there will be, there will be like a power and a common pin on these. And so what happens is, and we don't see this in all the diagrams, but there's actually power that actually comes to these pins. And so they can be powered, in this way. So what you're really thinking about, we're looking at, think of them, you can almost think of them as small relays, but that are a little bit more sophisticated than a regular relay. So one example that I'll give you that will be confusing if you don't understand that the gate actually it can have a power supply to it, is this. Now I'm going to show you this in a little bit more detail later, but let me just show you this right here. This is called a NOT gate. And the way that a NOT gate works is it only has one input and one output, of course. And the way that this works is if your input is 1, which means, now we're talking about 5 volts here, okay? So you apply 5 volts to this pin, then you get 0 volts out, or a 0. And we would say that this one is high and this is low. So when you put in a high, you get out a low. Now we can kind of picture that. That's not bad. But what about this condition? When we put in a 0, which is 0 volts, we call this low. Guess what happens over here? We get a 1, which is 5 volts, and we call it a high. And so the question always comes up right away, if I haven't described the power idea to you, is what? How can you get 5 volts out when you're putting nothing in? So realize this is just the input and the output, but this thing actually has a power supply. And so, it's really just making a decision and then either passing the power on or, passing the voltage on as a signal or not passing it on as a signal. So just be aware, the gates actually are connected with a power supply. So let me get rid of this. And we're going to move on and we're going to take a look at this AND gate. Now, what an AND gate, the way an AND gate operates is this. It's the idea that in order to make this output high, I need to have a high on this input, which is A, and this input, which is B. So I have to have both of them. And so what that means then is that if A and B are high, then Y is high. And there's something that we do, which is called a truth table. Very, very important for these type of things. When we're looking at gates, truth table tells us a lot. So I'm going to show you how to make a truth table. Now, if you think about it, how many different options are there? How many different combinations of input conditions? Well, I could have it where A and B are both 0. So I go, okay, I'm going to write that down. So A and B in a table, okay? And I'm going to go like this. Well, I could have 0 and 0. I could have it where A is 0 and B is a 1. Or I could have it where A is a 1 and B is 0. Or I could have it where they are both 1. Now, when I say 1, this is just a digital form of saying there's 5 volts or 0 volts. And we could also just say high or low, okay? High or low. So both low, B high, A low, A high, B low, A and B high. Now, what a truth table does is it actually tells you, based on these conditions, what the gate will do. In other words, what will happen at Y. So let me explain it. Now these truth tables are going to be based pretty much on how does this thing work. And as I've just explained, if 1 and 1 are high, then Y will be high. Now, is there any other condition for this gate where this Y will be a 1? And the short answer is no. 1 and a 0 does not satisfy my AND condition. 0 and 1 does not satisfy it. 0 and 0 do not satisfy it. So that means that it's 0, 0, 0, and the only condition that will give me a high output is when A and B are both high. Okay, so that gives you an idea of the truth table for the AND gate. Now, this is the part that I like. It kind of helps you to understand, and it's where I show you the actual circuit. Now, if any of you have taken a look at the SCORM project on logic, there's some really good examples in there. Hopefully you've had a chance to look at that. So here's what a control circuit would look like that we would have built using buttons. This would be button A, and this would be button B. And these are push buttons. They're placed in series with each other. This goes to a relay. And there's my neutral. Now, in terms of ladder logic, we would be looking at probably 120 volt control power across here. And so when this relay becomes energized or de-energized, then we would go from here, we would have a contact, and the output I'm going to call Y, and it's going to be a light, and it's tied to the neutral over there. All right. Now, if you look at this circuit, what you're going to notice is that if you're not touching either one of the buttons, then this relay is de-energized. This contact is open because this is an R contact, and the Y is not on. Okay, it's not on. And so what we say is, in terms of input, this is 0 and this is 1. This is 0 and this is 1. So this is how we can compare it to our truth table. So we're not pushing either button, 0 and 0. And you can just look at this circuit and see what happens. You push button B down, but not A, still an open circuit here. You push A down, but not B, so you push this and close, this one's still open, still an open circuit. You push A and B at the same time, this contact will then close and your light will come on. Okay, and so this is a way of taking, a mechanical circuit and putting it together and seeing what it is. Now, this concept right here is the idea of series buttons. Series buttons. Now, this is actually a fairly useful circuit. You'll see this in terms of safety, a safety circuit for equipment with potentially dangerous crush zones. So in order to operate a piece of equipment, you actually have to use both hands on buttons that are far enough apart that if you're pushing the buttons, you're not going to be losing an arm over it, okay? And so that's the idea typically of these circuits. So series buttons, and so it's this and this must be pushed in order to make it go. All right, let's move ahead then to the very next component, which is an OR. Okay, and I'm going to leave a little bit of my circuit there because it'll be easy enough to use that again. Truth table particularly, because these are the standard conditions that we get if we have just two inputs. Now, the OR gate looks like this. A little bit concave on the left-hand side. Comes down like this. Here's my output. I'm going to call this Y. Here are my inputs. I'm going to call these A and B. Okay, A and B. Now, here's the understanding of the gate itself. An OR gate, the way an OR gate works is that if you have a 0 on both inputs, then you will get nothing for an output. So it's going to be 0. 0 and 0 is 0. If you have A but and not B, so A but not B, then your output will become high. If you have B but not A, your output will also be high. And interestingly enough, in this case, if you have 1 and 1, your output will also be high. And so this gate looks like this. 0 and 0 gives you 0 on your output. 0 and 1 this is where it's the one or the other one will make it high. Okay, that's good. Here, one or the other one will give you a high here. And here we have one or the other one, or this one or the other one, which is really both, and that gives you a high as well. Now this one will be easier to understand when I show you the actual motor control circuit. It looks like this. I'm going to extend this line just a little higher. Looks like this. Here is A. Here is B. And here's my relay. Okay, here's my contact, R, and here's my light. Now, let's take a look, A and B. Now remember, we need to give the conditions here, which is 0 means we're not touching the button, 1 means it's closed. 0, not touching, 1, we're pushing it, okay? So 0 and 1. So 0 and 0, we can see that, yep, nothing going through to the relay. 0 and 1, well, as soon as we push down on B, we're gonna have continuity. We're gonna supply voltage to the relay. It's gonna close, and the contact is going to close, and the light is gonna come on, okay? What about if we go the other way with that? We let go of this button B, but we push A. Same result. We're going to energize the relay. This is going to close. The light's going to come on. Now, what difference does it make then if we push both buttons at once? Well, if you push this one and this one, you now have two parallel paths. Honestly, the only difference that would happen in reality is if you did this. If the current going to this relay was 200 milliamps, when you push both buttons, you'd have 100 milliamps here and 100 milliamps here. But other than that, no other difference in terms of the output, okay? The output is just quite simply, this is gonna be closed and your output's gonna be on. So when you look at this one, the truth table actually helps a lot in explaining the actual, when you look at these two, comparing them, it helps a lot to see the truth table beside the actual ladder logic. Mechanical relay, the way we would have drawn this up for a mechanical relay. Okay, now let me move this and let's take a look at the next one. Now the next one, a little different. I already sort of gave you a sneak preview of this one. This is called a knot. The bubble on the end, input, output. Now you can see this is not really a decision making between two inputs. It only has one input. But every time you get a signal, it just inverts whatever that signal is. So let's look at it this way. This is a 1. That means this is a 0. This is a 0. That means this is a 1. And so there's not much of a truth table for this. It really just looks like this. And we would say in and out. We could have 0 in and we get 1 out, or we could have 1 in and we get 0 out. That's literally the truth table for this device. Okay, very, very straightforward. Now, this gate comes, you can get this gate really just on its own as a NOT gate, or it is sometimes combined with another gate. And so in terms of the actual different components, I'm going to make a list of them here as we go. So we've talked about this one, okay? It's the AND. We've talked about this one. This is the OR. And we've talked about this one. This is the NOT. Okay, so we know the rules now for those three. Now let's take a look. The very next thing we're going to do is a gate that is, you know, produced commercially in mass amounts, and this is called a NAND. And so this gate is literally built as one unit, and it combines an and a NOT in one component. And this is how it looks. They put the invert on the output side. So here we go. Here's A, B, and Y. Okay, A, B, and Y. Now the first thing we want to do is we want to make a truth table for this. And if you refer back to the truth table we made for the AND, you're going to notice something right away. A, B, and Y. 0, 0, 0, 1, 1, 0, 1, 1. Those are the options that we have in terms of what input we put into this gate. Now, if we put in 0, 0, the way that you need to think of this gate is like this. Inside here is the fundamental characteristic of the gate, right in there. So this AND is always going to do the same thing, whether it's a NAND or an AND. Inside here, it just says, do I have this input and this input? But this gate, because it's actually built with a built-in NOT on the end of it, what happens is it then says, well, if I get a 1 and a 1 here, I'll make this a 1, and then the output will be a 0. So let's go ahead and let's look through this and see if this makes sense. If I have a 0 and a 0, that means like this, right? 0, 0. And when I go inside of this thing, and here it is making its decisions, it goes, well, I'm an AND. And if this is 0 and 0, then this is going to be 0. And then the output end of it goes, oh, whatever you just said, I'm going to change it. And so the output is actually a 1. Okay, so this gate, there's a lot of decision making that goes on in there, right? Now, a 0 and a 1. Well, what happens with a 0 and a 1 is that will give you a 0 in a regular AND, and so this is a 1. A 1 and a 0, so a 0, 1, now I have 1, 0. That also gives you a 0 in an AND. It's not enough to satisfy it internally, and that becomes a 1. Now, let's look at this one. This is where the change happens. If we go here and we put 1 and 1 like this, now that goes into this gate and goes 1 and 1, and inside it goes, oh, I'm an AND, that works for me. And so it makes this a 1. And then the output says, oh, you're a 0 now. And there you go. And so what you're going to notice is that this gate literally produces the exact opposite effect of an AND. And but this is considered as one gate. Okay, so let me just put this up. Here we have, this is now a NAND. It's a NAND. Now I'm going to show you how we would do a relay circuit for this. Okay, with push buttons and a relay, and it would look a little bit like this. You're going to see it's not too difficult. What we really are doing is this. Line 1, neutral. Oh, this is an AND, so that means I need to have a couple of buttons. in series, okay? Because the AND is really a series circuit. It's like a series. There's my relay. But here's the difference. If I have an invert in here, that means that whatever happens, 0 and 1, 0 and 1, whatever happens in my input side is going to be inverted to what it would have been otherwise. So when I go 0 and 0, I know that this gate actually goes 1. What would I do over here if I wanted to produce this exact same effect in a relay circuit? How would I do it? Well, I would go like this. I would make this a normally closed contact, and then this would go over to the light like that. And what that means, if you look carefully, when this is de-energized, this contact is closed, which means that the light is on. Now, when is it that the light could be on? Well, the light will be on as long as the relay is de-energized. How long will this be de-energized? Well, the only time that this is going to get energized is when I push both buttons. So if you look down here, you go, oh yeah, 1 and 1 finally energizes the relay, opens this normally closed contact, and the light goes off, and there's my output at 0. So you got to understand, it's really just, what are we doing? Because the invert was on the output side, we simply changed this to a normally closed contact, right? Now, let's see, we should be developing a pattern here by now, so let's take a look. What's going to come after the NAND? What will come next? And so I think let's go ahead. This probably won't surprise you a whole bunch. This is going to be a NOR. Okay, essentially a not or. So it's the opposite of an or. So what we have to do then is we need to put some leads on here. This is going to be input A and input B, and this is going to be my output Y. So realize again, the inner workings of this gate are essentially identical to an OR. It's just that this invert section, which is built right into it, is going to change it up. Whatever we decide here is going to get changed up there. So we do it like this. We go, I'm going to write the table right here. We're going to go A, B, and Y. And here's my columns right there. So I've got 0, 0, 0, 1, 1, 0, and 1, 1. Now, if I put a 0 here and a 0 here, we know that the OR basically will kick out a 0 on the other end. 0 and a 0 gives us a low. So low and a low gives us a low. But this gate goes, oh, that means that I'm going to have a high output. Now, I'm going to clear that off, and let's take a little look at what happens next. We go 0 and 1, 0 and 1. So I'm going to put a 0 and a 1. And now with an OR, a 0 and a 1 inside says, whoa, that's exactly what I want, one or the other one. This is going to be a 1. And then the output says, oh, that's now a 0. So this becomes a 0. You switch it up with your opposite leads, you're still going to have a 0. You put a 1 and a 1 in here. 1 and 1 also gives us a regular OR. A 1 and a 1 gives us a high. So that means that if this is high, this is going to be low. And so there you go. There's your truth table right here. Truth table for the NOR, or the not or. And in terms of the electromechanical circuit, control circuit, it would look like this. A, B. Okay, so this is A and B, 0 and 1, 0 and 1. I'm going to connect these lines together. I'm going to run this to a relay and to neutral. Now, there'll be a contact here, and this is going to be the light. Now, what's the condition of the light? Well, first of all, what contact do we need here? That's the question. So seeing as this is really the opposite, in what condition do we want the light to actually, this output to be on? Well, it's going to be all the opposites of this. And so we look at this, we go 0 and 0 is supposed to give me a 1. The light should be on. So what am I going to do here? I've got this is 0, this is 0. That means this relay is de-energized, but the light has to be on. So we go, okay, if the light has to be on, then we're going to have to make this a normally closed R contact, all right? And that's what you're going to do in your, in your control circuit. And now you can see, if you follow through, you can see, you can follow all of these by looking at these two buttons, and it should really make sense. If you have a 0 and a 0, this will be on. Press either one of these buttons or both of them, and you're going to energize the relay. As soon as you energize the relay, this contact opens and the light goes off. So that means that all three of these sets of conditions are going to give you an output that is low or 0 volts. Okay, so there you see the electromechanical compared to the truth table and the symbol. See them all together. Now, what do we have? We're up to the NOR. Okay, this is the invert and this is the NOR. Now we're getting close. There's not much more to do. These are the basic building blocks. These are the building blocks of digital logic circuits, okay? Now, some of you may have, this may have already crossed your mind. You might be thinking about this. Let me show you a certain condition. And I want to start with this one. Let's look just briefly at an OR. Okay, now this is an OR, and I want to look at the truth table. Okay, so let's just I'm going to re-put this up. This is going to be A, B, and Y. It's going to be 0, 0, 0, 1, 1, 0, and 1, 1. Now remember, with an OR, if you have a 0 and a 0, you get a 0. If you have a 0 or a 1, you get a 1. And if you have a 1 or a 0, you also have a 1. But here's the thing that started to become an issue. They said, well, this 1 means that this gate definitely had one of the inputs and not the other one. One and not the other one. And this one represents a situation where you have this input and not this input. So it's definitely one or the other. Now, what would happen if, in this case, if we give both of these, we still get a 1, but we don't really know by the output whether we actually had only one or the other one. So it could have been one, could have been the other one, or it could have been both. And we don't know exactly which way it is. Now, if you needed to know, you would probably need another gate. And so that's what they designed. And this gate looks like this. It's also called an OR, but it has an added feature. This is an OR, and there's an additional line on the symbol, and it's called an XOR. And the X stands for essentially exclusive OR. So what that means is if I put my inputs on here and my output on here, if I get a 1 over here, it means that I have either this one and not this one, or this one and not this one. But if I have both, then I won't get a 1, I'll get a 0. And so this one has a little different truth table, and it looks like this: A, B, and Y. So a 0 and a 0 gives me a 0. A 0 and a 1 gives me a 1. A 1 and a 0 gives me a 1, and a 1 and a 1 give me a 0. And so you can see now that this gate, I can definitely differentiate between whether I have only one signal input at a time, and if I have both on here, then it's actually going to be a low output. So it's a way of saying, you know, it's exclusively one or the other one. So the exclusive OR, and its name, of course, the XOR, okay? So let me add that to my list over here. I've got this XOR. It's just really an OR, but with an additional line on it. XOR. Now, as you can imagine, we might continue this pattern for just one more component, and sure enough, we did. And this is the last one I'm going to show you. And by this time, you know, by the time you've been following through these components, the name of this one pretty well is probably what you're doing. And this is the XNOR. That's usually what people are doing by the time we get here. Okay, XNOR. And this one looks like this. It's the typical XOR, like this, but with an invert on it. Okay, now this is a single component, and it follows all of the rules of an XOR, but it includes a NOT, and the NOT is built into the output. Okay, so let's do the truth table for this one. A, B, my inputs right here. Y is going to be my output. Y right there. Now I can put in a 0 and a 0. I can put in a 0 or a 1. I can put in a 1 or a 0, or I can put in a 1 or a 1. That can, you know, we can physically line it up so that those are the inputs that get applied here. Now, remember, this is an exclusive OR, so let's see what happens. A 0 and a 0 in an exclusive OR gives me a 0. But, hang on a second, we have a built-in not there, so that makes this a 1. Now, if I take this OR inside of here and I go, now I have a 0 and a 1, that's where this XOR goes, oh yeah, I know what to do with that. A 0 and a 1 means it's a 1. And then the invert goes, oh, okay, you're going to be a 0. Now, if we go to the 1 and the 0, it does the same thing. 1 and a 0, it goes, oh yeah, I'm happy with that. I'm going to make this a 1. And the output says, no, actually, you're going to be a 0. Now, when we put in a 1 and a 1, this gate goes, hey, I'm an XOR. A 1 and a 1 doesn't work for me. I'm going to make you a 0. And so the output goes, you know what? You're actually going to be a 1. And that is what the truth table actually looks like for this gate. Now, let me show you the table. The table, or I should say the circuit. Okay, the circuit that I would build, and I'm going to make this. This is actually for the last two. Okay, and I'm just going to modify it slightly. So this one is going to be for the XNOR, and I didn't draw this one for the XOR, but I'll just show you a quick modification. So this drawing right here is going to be for this XNOR, this one we have right here. And it essentially looks like this. We start with an open button, and then we have a second line, and that switch is mechanically tied, okay? Mechanically connected. Then we're going to go over to another button, and down here we have another mechanically tied switch. Now, this one is going to be A, and this button is going to be B. And from there, I'm going to move over, I'm going to tie these together. I'm going to go to my relay and tie it in there. Now, let's take a look at this circuit and see what happens. I'm going to put a contact in here first of all. And before I finish the contact, let's talk about the truth table and see what we should do. So let's look at the truth table. The truth table says that if I have a 0 on A and a 0 on B, that my output should be high. So I go, well, if I don't push this, that means this is going to be 0 and 1. And down here, this is going to be 0 and 1. And this is where the buttons are, right? This is just an auxiliary sort of line that's going to be operated by the same button. So 0 and 0. So not touching A, that means there's no continuity through this line. However, at the same time, this is open, so there's no continuity in this line. So we go, okay, that means this is de-energized. We go, but wait a minute, the light is supposed to be on. Oh, okay, this must be a normally closed R contact. Okay, now we're done with that drawing, and now let's see how it operates. If we come along and we push on B, you can see that B will close, which will open the line with the A button in it, okay? So this will open, this will close. That will energize the relay, open the contact, and turn the light off. 0 output. What about if we just push button A? Sorry, I probably just did A. But in any case, whichever one you do, A or B, the next button that you push, if you push A second, this will close and this will open, which means now this line is open, but this line is closed. And so we can see that that's going to energize the relay, open the contact, and give us a low on our output. Now here's the neat part. What happens if you push A and B at the same time? Well, A, when you push this, opens the line going to the B switch. And when you push B, it opens the line between the A switch and the relay. So if you push them both at once, no energy in your relay, this contact remains closed, and your output remains high. And so you got to see the truth table has to match the actual wiring diagram. This is the comparison, right? So there you see the XNOR. Now, how would we make this an XOR? How would we make it an XOR? And I think what we're going to find is that the whole circuit is exactly the same, except that this contact, if we make it an XOR, this contact is a normally open contact, okay? That's the only difference between those two. So XOR, normally open. And if we move to XNOR, then normally closed, like that, okay? And it's actually a component, it's a hardware issue at that point to make sure that you get it to work properly. All right, so there we have, we've talked now about basically 1, 2, 3, 4, 5, 6 building block components. And you know what it really comes down to is these ones here are just recombinations kind of the and the or. And this is really just a specialty or. The last one we have, of course, that I just need to put here at the bottom is the X nor. And that's with that on it. Okay, so how many actual building blocks do we have, like just basic building blocks? Well, and, or, and not. So I would say that really those are the key sort of base elements. These ones are already, you know, they are individual components, but they have the not essentially built right into them. And so, you know, the next thing we need to do is and here comes the logic part, is that we need to draw some combinations up, and I'm going to show you how to solve a problem when it's basically, we're going to build a truth table for a combination that I'm going to just, you know, we'll make a couple up on the fly, and then we'll see how they recombine. So we can combine gates in different ways, and so let me show you an example. Inverts can be placed almost anywhere in a combination of gates, and so this part is kind of interesting to see how we do it. Let me show you how you might see this in a diagram. Okay, and I'm going to show it to you like this. Let's say that I had this and I did a drawing and it looked like this. Well, what we would kind of say is it looks similar to the NAND that we had, or the no, like an AND, but the NAND and the NOR, the invert is specifically always on the output, okay? So if you look at these components, the NAND, the NOR, and the XNOR, the invert is built into the device and it's actually on the output end, okay? So what we've got here, you'll see this symbol, but here's what it actually is, okay? It's actually this. Okay, there you go. That's the NOT. And then it goes like this. And here's your AND. Okay, so this and this are pretty much equivalent, but a lot of times it'll be written like this just to conserve space, because this gets a little strung out, especially if you have a few of these here and there throughout your drawing. So let me show you how I would solve this particular one. Now what we need to do actually is to build a truth table for this drawing. And so let me show you what we have. This is going to be A, B, and R, okay? Now, I changed it to an R mostly just because I got tired of Y. Okay, now if you take a look, what you have is A, B, and R. And the possible input conditions would be 0, 0, 0, 1, 1, 0, or you could have 1, 1. And so let's go ahead, and what I'm going to do, and I'll tell you right now, probably you have an advantage using a whiteboard when you do this, because watch what I do. I start and I go like this, 0, and I go 0. Now this represents this 0 and this 0 right here. It's like, okay, 0 and a 0. And so I'm going to show you actually on this one as well. Maybe I'll start with this one. It'll be easier to look at. If you have 0 and a 0 here, as soon as you get to the invert, this 0 turns into a 1. So that means that what actually arrives into the AND is 1 and 0. Now, 1 and a 0 on an AND doesn't work for anything, and so you get a 0, okay? Now, what if I had, and here's where the whiteboard thing works well, is watch this. Now, if you do these with a pencil, you can also make it work pretty good. Just erase your letters out of there. What about this? 0 and 1. And I'm going to put that the same thing here, 0 and 1. So this is how we're doing this one. This comes to the invert, goes into the invert as a 0, comes out the other side as a 1. This 1 goes in, it's a 1 there. This 1 goes in, it's a 1 there. Now what does an AND do with a 1 and a 1? And so, it goes, that's a 1. Output high. Now, I'm going to erase those, get those out of the picture. To some degree, some people say, well, you could leave some of the numbers on. I go, yeah, I guess you could, but it's pretty easy to get confused. So I normally just, to keep real clarity and step by step, I get rid of all the numbers and I just start with the next one. Here's a 1 and a 0. Now, if I put that here and I go 1 and 0, I go, this comes down the line to the invert, comes out as a 0, which means 0, 0, and 0, because an AND is going to give me a 0 there. Something interesting has happened with this. You can see what it's gonna be under normal circumstances with an AND. If we have a 1 and a 1, an AND will have a high output. So we've actually modified by putting this invert into here. We've actually changed which condition will give me the high on this AND, because this 1 and a 1 right here is going to come into here as a 1, come out as a 0. That means I'm going to get 0, 1, and that's going to be 0. So we've literally changed where we're going to get our high output condition on this device by putting an invert in one of the input legs. And so, there you go. But the only way to really be careful and do this truth table is to just work through it one set of numbers at a time and see what your output is going to be. Now, this will become fairly important, especially when we start combining 2 or 3 gates together, right? So with that being said, let's do a couple more examples. Now, this would be kind of an interesting combination. This would actually be, this is a NAND, right? A not and. I'm going to call this S just to change it up a little bit. This is going to be A, and this is going to be B. So let's go ahead and work with it, in place, right where it is. And let's go ahead and jot down some things. We remember what we need to do is make a truth table for this. So truth table. I'm going to put the truth table right here. A, B, and S will be the output. Now, 0 and a 0, 0, 1, 1, 0, 1, 1. Now this format, what we're doing here in counting out these conditions is actually the same way that we count in binary numbers. And so, you should hopefully see that pattern. This is something that we talked about earlier. Now, I'm going to start. You can see this could get pretty confusing if I'm not careful. So I'm going to start here with 0 and 0. I'm going to go, and then what I'm going to do is just inside the D, I'm going to actually put what the AND gate does. So if I put a 0 in, that means I get a 0 in there, inside of that little tiny gate in that semiconductor material. That actually becomes a low. This 0 becomes a high. That means that the AND says, no, not good enough. And because of the invert on the end, it becomes a 1. So it says, yep, make the output high. That's how that gate deals with that situation. Now, let's go ahead and I'm going to move to the next input condition. But first of all, I'm going to get rid of these completely. Okay, now moving to 0 and 1. 0 and 1. So 0 volts, 5 volts. Low, high, right? So we go, okay, this 0 comes inside here as a 0. This 1 comes through the invert, becomes a 0. That gives me a 0 inside of the gate. And now the invert says, yep, that's going to be a high output, high output. Now, let's take a look at 1 and 0. Here's a 1 and a 0. The 1 comes in here and becomes a 1. The 0 comes into the invert and is changed into a 1 entering the door. That makes the output a 1, but then the invert goes, wait a minute, you're going to be a low output. And our final condition, which says that I'm going to take a 1 and a 1. This will be a 1. This 1 will go into my invert, enter into the gate actually as a 0, which will give me a 0, which will then be the gatekeeper there on the other side is going to go, oh, that gives me a high output. Okay, so there you go. And this truth table, kind of specific to this device. This is not just a NAND. This is a NAND with an additional invert. Okay, so this is really a combination. It's a combination circuit between those two. All right, now, here's an interesting question. I'm not going to do this for everyone, but I do want to show you how to do it. How would this look if I was doing this with relay components in a 120 volt circuit? And I'll show you how I would cipher what I was going to do, line 1 and neutral. So I go, okay, what I'm going to do is it's an AND, right? This is an AND. And so I know that the first thing I need to do is put two switches, two buttons in series with each other, but don't put a contact on them yet, okay? Don't put a contact. And then this is going to come to a relay like that. And then I'm going to have some kind of a contact here. I'm going to put the normally open because it's easy to change to a closed, and I'm going to show the output. Now, what I have is this. How am I going to make this match this truth table? Okay, because that's really this little tiny device the size of, you could fit quite a few of them probably on a pinhead, would actually have been replaced by a physical circuit with buttons in it. And we want to know what these buttons look like. So this is going to be A, and this is going to be B. Now A is straight up. It's just like if it's a 1, it's actually high. And so I'm going to make that like this. Okay, that button's going to be like that. B is actually the opposite. So think of it this way. It's because this is 0 and this is 1, right? If B is 0, what actually happens in here? Well, that becomes a 1, right? So we do this when we're drawing this. We make this a normally closed button. If there's an invert on the input, we use a normally closed button to represent this. And you're going to see operation-wise why it works, how it works like that. Now, when I get a 0 here, I actually want a 1. Oh, okay. So that means I need to make this contact normally closed. All right. So let's take a look. What happens if I have, so we're going to start with 0 and 0, okay? 0 and 0. So I'm going to get rid of this. And we're going to now look at this and compare this to our truth table, okay? So watch carefully. 0 and 0. That means I'm not pushing this button, and this is 0, and this is 1. So when the button is pushed down, it's a 1. So right now I have 0 and 0, which means that no continuity here. This is closed, but seeing as this is open, this is de-energized, this is closed, and my light is on. There's my high output. Okay, now let's move to the next one. I'm going to take this off like that. Now we move to 0 and 1. So this stays at 0. I push this down, it becomes a 1. Now I have 2 breaks in that line. Definitely that's not going to get energized. So that means this will remain closed. My light will still be on. Okay. Now let's go ahead. I'm going to get rid of the lights. Let's see what happens when I move to 1 and 0. Well, 1 here means that I'm going to push this down and it's going to make contact. 0 here means I'm not touching this, so it's going to remain closed. This is going to energize. That's going to open, and my light is going to be off. And there's your low output. Now, what happens if I go to the last condition, 1 and 1? Well, if I push this one, it makes, but if I push this one, it's open, leaves this de-energized, which means that this contact remains in its closed position, and the light is going to be on. Okay, so that's how we compare an electromechanical ladder diagram with the truth table. So we can make one of these up for any component that we can draw. It's just thinking in terms of those control circuit terms. I think a few more examples will be a good idea. So let's take a look at this. Here I have, it looks to me like just a regular OR gate. Okay, it's just an OR, but it does have an invert placed in line with the B input. And so we need to draw it like this. And I'm going to go 0, 1, 1, 0, 1, 1. Now, remember, this is just a regular OR. So what normally happens with one of these is that the things that will give me a 1 right here are when I have 0 and 1, 1 and 0, or even a 1 and a 1, because this is not an exclusive OR. So any of these last 3 conditions are going to give me a high output. So let's take a look. Now this invert is going to change things up a little bit. And so let's start up here. Let's go 0, 0. Now normally a 0, 0 with an OR would give you a low. But in this case, this 0 is going to go into this invert and become a 1. And that's going to make this high, like that. Now, if I go with a 0 and a 1, what's really going to happen, I'm going to get rid of those. So that 0 is okay there. We haven't changed this condition, that A condition. But for the 1, I need to make this a 1, goes into here and becomes a 0 here. Now, what does a 0 and a 0 give me on any OR, exclusive or not? It's a 0. And so there we see the 0. Now, going to get rid of those. Let's look at the next one, 1 and 0. Well, 1's going to go here. 0 is going to go into this invert and become a 1 inside. That is going to make this. Now remember, if this was an exclusive OR, this would now be a 0. But because it's just a regular OR, this is a 1. And so 1 and a 0 actually gives me, 1 and a 0 gives me a 1. Now, what about a 1 and a 1? So I go 1 and a 1, and what's that going to show for me? So I go, well, this 1 stays as a 1, this 1 becomes a 0. Now 1 and a 0 still gives me a 1 with an OR, and so look at that. There you have the truth table for that particular gate. And so if I was going to do a, now let me show you this one, because these are not too bad, and it does give you a little bit of extra understanding. What would I do if I wanted to make, if I want to wire this up with a couple of push buttons and a relay? What is the, what's the conversion in electromechanical components to this? Now, I keep saying, what is the conversion? In fact, what's happened is these were the circuits that have always been used, and there are many of them still in use, and you will find yourself still having to understand and deal with and work on actual control circuits with relays and buttons, okay? They haven't disappeared, and they're probably not going to for a long time. So you do need to sort of understand this stuff. This is from motor controls, but now these components, these tiny electronic semiconductor components, are doing the same thing as what used to take, a control cabinet that you could comfortably live in for probably for a couple of weeks anyway. And so, the things have just gotten so small that it's really incredible. Now let's take a look then. This is an OR. Now when we see an OR, we have to think parallel. And so we're going to have a button here. We're going to have a button here. And then these are going to combine together. This is going to go to a relay. And here I'm going to have a contact that will determine what happens with my output. Now, before I finish these, I want to look at what I really have, okay? Now, the first one in this case is, it's just a regular input, no invert on it. So I'm going to make this button, this is going to be button A, normally open. So this is 0 and 1. This button is going to be button B, and it's going to be normally closed because of the invert in that leg. And now you're going to see this is 0 and that's 1. So if I push on that, it's actually going to open that switch, okay? Now, because there's no invert on the end of this, then I'm actually just going to use this normally open contact. Now let's try and take a look and see what happens. Hands off the circuit, apply 120 volts, nobody touching any buttons. Is the light on or off? Well, because button B is a normally closed button, that means the power is going to be available at this button. Current will flow through this relay, and it will then close this normally open contact, and the light will actually be on. Okay, so nobody touching any buttons, the light is on. Now, if somebody comes along and pushes button B, what happens to the light? Okay, we're now pushing on button B. This is held open. Relay becomes de-energized. This contact opens, and the light goes off. and that actually matches your truth table. Very important that whatever you do with your push buttons matches your truth table. That way, that's how you know you're getting it figured out. Now, I let this button close again. Okay, now nobody's touching it. And I push on this button. So I close A. Well, now I just have parallel paths to my relay. My relay is energized. This contact is closed and the light is on. What would happen if I'm just pushing button A and then I push button B, which is actually a normally closed button? Well, nothing much, except that now all the current of the relay will go through button A instead of being split between the two. But the overall outcome is that this relay will still be energized, this will still be closed, and the light will still be on, and you'll see that reflected in your truth table. All right. Good. Okay, now we're ready to move on to the next thing. This is the last kind of thing that we're looking at with logic gates. I want to show you how to combine, 2 or 3 or 4 gates together, and how we're going to build a truth table for it. So let's take a look. Okay, here I've combined 3 gates together. I have an AND gate, an OR gate, and I have a NAND. Okay. And I'm basically connecting these 3 up. I'm only using 2 inputs to actually feed into both of these gates. And so here's the way that we look at it. Whatever this input is will be experienced, of course, by both gates. So if I start with 0, 0, I'm going to go like this. This is 0 and 0. And that, of course, gives me 0 and 0 here. Now with an AND, that means I get a 0. With an OR, that means I get a 0. And so these are 0 and 0 coming into this AND. Now inside of an AND, that gives me a 0, so my output is actually 1. Output is 1 at M. Now, I'm going to clear those away. And then what I'm going to do is I'm going to give you the next condition, 0 and 1. So 0 and 1 coming from these are my this is 0 volts, 5 volts coming on my inputs. This comes in as a 0 and a 1, which makes a 0. This comes into here as 0 and 1, which makes this a 1. Now a 0 and a 1 coming into here still gives me a 0 because this is an AND, and that means my output is still 1. Now, let's go ahead and look at the next condition, 1 and 0. Well, if this is a 1 and a 0, that's a 0. A 1 and a 0 makes a 1. This is now 1 and a 0, which is still a 0, so this is still 1. Now, the final condition is 1 and 1. So that gives me 1 and a 1, which gives me 1. Now with a regular OR, a 1 and a 1 also gives me 1. And with an AND, a 1 and a 1 makes a 1 inside, but because of the invert, my output is low for the final condition. So the actual truth table, because what we're being limited to here is 2 inputs, even though we're running it through more gates, 2 inputs and 1 output can always be described in a truth table with 4 conditions, because we can only get, if you only have 2 inputs, you can only have 4 different conditions. That's it. And so what I'm going to do next is I'm going to show you a different circuit, a little bit different. And this one is going to, it's not the kind of thing that you'll be able to just guess probably off the top of your head. You're going to want to actually work through this one. And it looks like this. I'm going to put in an AND gate right here. And I'm going to also put in just down here an exclusive OR. Now, an exclusive OR means it has to be a 1 and a 0 or a 0 and a 1 to give me a high output. Now, the output of this and the output of this XOR are going to come like this. They're going to feed into another gate, but there's going to be an invert on this one. And this is going to be, and it's a gate that's going to be actually a NOR. So you're going to see that this is actually a NOR indicated by this invert with an invert on its A input. Okay, and this is going to go out, and I'm going to go back to using Y. What I'm going to see over here is A going in and B going in, A and B. And I'm also going to take, I'm going to take this input from A and I'm going to feed down and use it as one of the inputs on this XOR. The other input I'm going to bring from here, and this is going to be input C. Now, the first thing that you need to do is, before you can make this truth table, well, it's the process really of making this truth table, is you need to say, what are the possible conditions that I could have? And so I would say, well, I've got A, B, and C inputs, and my output is Y. So I can really look at it, I can say, well, what could really happen here? Now just count with me, just count as you would count if you were counting in binary, but just use 3 positions. So it would be 0, 0, 0. That would represent 0. Then you'd have 0, 0, 1. That would represent 1. 0, 1, 0 would represent 2. 0, 1, 1 would represent 3. 1, 0, 0 would represent 4. 1, 0, 1 would represent 5. 1, 1, 0 would represent 6. 1, 1, 1 would represent 7. Now, I think that that covers all of the possible input conditions. We've had all the conditions that could possibly happen with these 3 inputs. And so that's enough. That's as far as we have to go. Now, let's take a look and see what that does for our output. And let me show it to you like this. 0, 0, and 0. That means 0, 0 here, which gives me a 0. Look at them one gate at a time, okay? 0, because A is 0 and C is 0. So 0, 0 there gives me a 0 here. This comes in, and this is now 0 coming in, but 1 inside of that OR. This is a 0, and it just goes in there as a 0. Now, what do a 1 and a 0 do with a regular OR? Well, this exciting stuff, they make it a 1. But you've got an invert which says, no, you're going to be a 0. And so our first output condition for the first set of circumstances is actually 0. Now be patient and let's carry on to the next condition. Zero, zero, one, 0, 0, 1. Now remember, this 0 on A also comes down here as a 0. So I've got 0, 1. 0, 1 on an exclusive OR gives me a 1 output. 0 and 0 here give me a 0. That means that this 0 comes in here as 0 and becomes 1 inside. This 1 comes over here and it gives me a 1 there. Now this is not an exclusive OR, it's a regular OR, so that means I get a 1 here, which becomes a 0 at the output. I was starting to think that one was going to work out. Okay. Let's look at the next one. 0, 1, 0. So I've got 0, 1, 0. That makes this a 0. This is A. So this is a 0. This is 0, and this is 1. That makes a 0 there. 0 and 0 makes a 0 here. This makes this a 0, and I have 0 here, and this becomes 1. This becomes 1, and that's still 0. Still 0. No output. You know, at some point, if you're looking at these, you can start to think, and this is where the sort of the critical thinking comes in a little bit. If you start looking at this, you go, what on earth would actually make this a 1? What would make this a 1? So you think about it, you go, well, this could be a 1 if this will the only way this can be a 1 is if this is a 0. And how can this be a 0? Well, the only way that this can be a 0 is if this is a 0 and this is a 0. So you go, huh, that's interesting. So if this is a 0, this has to be a 1. How can this be a 1? What can make this a 1? Well, this can only be a 1 if this is a 1 and this is a 1. And how can this be 0 if it's an exclusive OR? Well, a 0 and a 0 could make this a 0, but we already looked at that one. What's the other thing that could make this a 0? A 1 and a 1. So you go, oh, wait a minute. So if this was 1 and 1, this could be 1. This could be actually 0. Say, oh, okay, perfect. That means that if A, B, and C are all 1, then this can actually be a 1. And so, in fact, we could go down this whole list. You can prove it every one at a time, one at a time. I'm not going to do the whole thing because you guys have lots of paper and a fair bit of time. And so you can run through there, but I can tell you right now, the only thing that is going to make this a 1 over here is if A, B, and C are all high. Okay, and this is where the idea of logic comes in. All right. Now, what I do want to do is I want to show you one more thing. And then I'm going to leave you with kind of a quiz question for you to do. And but first of all, let me just show you something called a timing chart. Now, for any of you that have ever, and it relates quite closely to logic gates as well in their understanding of it. This is what a chart looks like. Now, I'm going to first of all, I'm just going to show you a gate, and I'm going to show you a gate that looks like this. And I'm going to put an invert right here. And then I'm just going to leave it at that. I'm going to say this is A, B, and what have I not used yet? V, okay? It's V. So we go, what would the chart, what is a timing chart and how does it look? So here's the way that we typically would look at it. This is going to represent time. And this little, this space right here, this is going to represent 1 and 0. And this is going to be for A. All right. And then I'm going to go down here. I'm going to make another little zone right here. Okay. And I cross this off so you know this is just in between. Okay. We're not using that space. This is going to be 1 and 0. And this is going to be B. Now we're going to make another little space here that we don't need to use. And this down here, now remember we only have 2 inputs and 1 output. So this is going to represent 1 and 0. And this is going to be V. So our output. Now, if we start, we usually start by looking at our truth table. And so what I'm going to do is I'm going to just quickly make the truth table because we want to compare this. And so this would be A, B, and V, right? And if this was 0 and 0, that would make this 1 and 0, which would make that 0. If I had 0 and 1, 0, 1, and 1, that would make this 1 because of that invert there, right? Now, if I had a 1 and a 0, 1 would make that 0 and 0. This would be 0. And if I had 1 and, the last one would be 1 and 1. So 1 and 1, that would be 0, 1. So that would be a 0. So there's only one condition that actually turns this on, and that's when we have 0 and 1. Now, here's the way that we look at it. We start with this condition, and we want to graphically show what is happening by looking at a timing chart. So we start through time and we say, at this instant in time, we're at the point where we are with 0, 0, and 0 condition, 0 and 0 conditions on my inputs. So we go like this. I'm going to draw these lines like this. We're at 0 and we're at 0 like this. And if that's the case, what is the condition of my output? And I see it in the same condition. Now, this would be considered an event line right here, okay, on my timeline. And I'd say, okay, at this point, B becomes 1. So the way you draw it is you go like this. B goes up, and now we continue through time in this condition. So B is now a 1. A is still a 0. But when that happens, my output becomes a 1. And so you'll see it raise up, and it'll follow through the graph in the 1 position. Now, when I get to the end, here's something that interesting that happens. A becomes high, B goes low, and when A is high and B is low, my output is low, so I now have to show my output going low again. Okay? Now, I move to the next condition. So I have 1, 2, 3 conditions. This is the last one, 1 and 1. So A is high right now. B moves back high again. And we move through some time. A is still high, B is high. And what happens to our output? Well, it stays low. So what would I have to do in order to change this all up again? Well, I'd have to move. Really, the only way to get the output to go high would be to go like this. I would have to make, at this point, I would have to make A low and leave B high, and my output would become high again. See, so you could continue all day just changing these inputs back and forth, and it would scroll out this little graph. And it's based on time. These are called timing charts, and it's kind of function charts. So what happens is these type of charts are often because they show events as it moves through time, what will happen. And these are often shown with relays to show what different modes of relays will do, especially timing relays. Okay, so very valuable to be able to look at this kind of chart and understand, try to draw it out and understand what's going on. So you're just really looking through time at these conditions, starting with one condition, moving to the next, to the next, to the next, and graphing it, okay? So it's a graphical chart of a truth table, really is what it is. Okay, so I just have one thing that I'm gonna leave you with, and what I'd like you to do is spend a little time on it. It's gonna be a combination logic circuit, and I want you to work through it. And we'll you can ask about it the next time we have a Zoom discussion, and we'll talk it through there, and the answer will be available there. All right. So hang on a second. I'm going to draw it up for you, and then we'll conclude. Okay. This one's for fun. Okay. And so these are, once you get onto these, they're actually quite interesting. They're like little puzzles. If you like puzzles, then you like this sort of thing. What I'd like you to do is just take this and create a truth table for it. Now, you know that seeing as you have 3 inputs, your truth table has to go all the way from 0, 0, 0, all the way to 1, 1, 1, and every combination that you could have in between. So you'll need a truth table with all of those all the input conditions all listed in order, and then determine just by going through it and applying what you've learned now about how these gates actually operate, and go ahead and figure out what the output E is for each one of those input conditions. And we'll talk about it. We'll talk about it when we get together in our discussions. All right, we'll look over what the answer is now. That basically concludes our conversation on the logic gates. So please look in the handout section, and you're going to find a document with some practice on this, and you're going to need to practice kind of all the aspects that we've really looked at, I would say, particularly including even looking at a symbol and drawing what the control circuit would have looked like that it would have taken to build that particular logic gate. And it gives you a pretty good understanding of what's going on in the logic gate. If you can't compare it to that circuit, then the logic gates don't really mean as much. So that's an important part of it. So please take a look at the practice, and then we'll carry on. I'm just going to give you a couple minutes at the end here. Well, maybe not a couple minutes, but a few seconds to take a look at that. Make sure you're able to get a nice clean shot of that circuit without me standing in front of it, just so you can basically draw it down and solve it.